You might have switched off a moving fan and have observed that the blades of the fan keep on moving for some time after switching the fan off. Or you might have seen children rubbing a toy car several times on a floor to rev it up and then allowing it to move along for some distance. Or you might have seen helicopter land and have noticed that the blades keep on rotating for some time even when pilot puts the engine off. All these are the examples of rotational inertia. In the case of linear motion, the object keeps on moving for some time even after we stop applying force on it. This is due to the inertia of motion of the object. Similarly, in rotational motion, the object keeps on rotating for some time even after the force is removed, and this is due to the rotational inertia of the object. The property of a rotating body which opposes a change in its angular velocity is called its rotational inertia. When the force causing the rotational motion of the body is removed, the body keeps on rotating for some time due to its rotational inertia. The rotational inertia of an object is also called the moment of inertia. In linear motion, Newton's second law gives the magnitude of the force required to change the linear velocity of an object in motion as per the equation F is equal to ma. Analogous to this in rotational motion, the equation for Newton's second law is tau is equal to I alpha, where tau is the torque acting on the body, I is the moment of inertia, and alpha is the angular acceleration. The rotational inertia of an object depends on the shape of the object and distribution of mass with respect to the axis of rotation of the object. For this reason, only the object rotating under effect of same torque but rotating around different axes of rotation have different rotational inertia. Here you can see that due to the difference in the distribution of mass and in the rotational axis, the rotational inertia of the objects is different. Also, higher the value of rotational inertia, a greater torque is needed to stop it. The rotational inertia or the moment of inertia of a body of n particle is given as I is equal to sigma mj rj squared, where j is equal to 1 to n, where m is the mass of the particle and r is its perpendicular distance from the axis of rotation. To understand the variation in rotational inertia, let us consider two identical thin rods rotating about two different axes of rotation. One is rotating about an axis passing through its endpoint perpendicular to it, and the other rotating about an axis passing along its perpendicular bisector. Now, each rod is provided with a force having equal turning effect. It can be observed that the rod rotating about an axis passing through the endpoint rotates for a longer time. This shows that it has a greater rotational inertia. Mathematically, the rotational inertia of the rod in these two cases is given as I is equal to ml squared upon 3 for the first rod and I is equal to ml squared upon 12 for the second rod.